can extend lifespan. And what we showed was that there's a set of genes that controls that process. This isn't just glucose hurting the cell. There's a genetic pathway that gets triggered by low energy. And these genes we talked about in last episode, they're called sirtuins. And there are 5 of these genes in yeast and 7 in our bodies. And they respond to low energy. They respond to other stresses as well, such as high heat, low amino acids, high salt. The sirtuins will get activated by these, what we call hormetic effects. What doesn't kill them makes them stronger. And in this case, low energy led to the activation of these enzymes called sirtuins. And then they took care of the DNA repair and also stabilization of the epigenome. Now,
there's a lot there. We got to back. Let's slow this down and pace this out. Let's start with sirtuins. What's actually happening when, in the case of yeast, or any organism in this case, because it's very similar mechanisms, right? What's actually happening with the sirtuins when yeast or any other model organism is calorie restricted, is fasted?
Yeah, well, their role is to extend the lifespan. So what they're doing down at the very minute part of the cell is they're protecting DNA and making sure genes stay on when they should be on. But what's happening to boost their activity during caloric restriction, this low glucose level, we managed to figure out in the first couple of years when I moved my lab to Harvard Medical School, or started my lab at Harvard Medical School, we found that low energy activates a certain gene. It has a name. It's called PNC1. We have an equivalent gene in our bodies called NAMPT. And turning on that PNC1 gene in yeast was able to activate the sirtuins because that gene makes a fuel for the sirtuins called NAD. And so in our bodies as well, when we're hungry, these genes come on that make more NAD, this very small molecule that the sirtuins need for fuel. And then they do the protection. They repair DNA and they stabilize the epigenome.
And this is sort of the beginning place that led to NAD boosters, where we started going, oh, well, if we can boost NAD in other ways. And that's not, we'll talk about boosters in another episode, but just to sort of put that in the chronology of how this revelation came about and why so many people are now taking NR and NMN.
Yeah, that came out of our lab. We found 2 ways to activate the sirtuins synthetically. One was to use the red wine molecule, resveratrol, plus some other plant molecules that are now used in supplement market. And that was a big craze in the 2000s from our lab. And then the second one, which is now probably an even bigger craze, is the NAD booster. And a lot of people are shooting themselves up with NAD or taking NAD precursor supplements. You mentioned NR and NMN. We'll get to those in another episode. But you can mimic low glucose in these yeast cells by giving them these NAD boosters. Or you can turn on this PNC1 gene artificially and they live longer in all cases. And we found that if we deleted that sirtuin gene in the yeast, either one of them or multiple ones, then caloric restriction in the yeast didn't work anymore, which told us that this wasn't just glucose being bad for you. Glucose doesn't hurt you. It's that the low glucose is activating the natural defense state of that cell, which we have inherited over the billions of years since we separated.
People are just going to cut out that little part where you just say, glucose isn't bad for you. And they're just going to play that on a loop, and it's going to be great.
All right, well, glucose is bad for you, but not for the reason that you might think.
So we have a little better understanding now of how sirtuins are turned on by fasting. We talked about 2 other classes of longevity genes in the first episode, mTOR and AMPK. Do you want to go really briefly through how these genes are impacted when we restrict calories, when we fast?
The first one is mTOR, which stands for mammalian target of rapamycin, the drug rapamycin. We talked a little bit about it in the last episode, but let's refresh everybody's memory. This is a protein complex in the cell that registers amino acids. When you have a lot of protein, you eat a big steak, it's going to activate this mTOR protein complex that causes the cell to build things. It's one of the reasons eating steak allows you to build more muscle, but that's not a recipe for longevity. What we know from many animal studies, even in yeast, if you downregulate the activity of this mTOR protein complex, you get longer life. Why? Because it's activating a process called autophagy, which recycles proteins. So when you're hungry, this autophagy will get all the old proteins, put them in the recycling bin, and then bring them out as fresh proteins. And that seems to be really important for longevity. In fact, even if you just inhibit mTOR and stimulate autophagy, that's sufficient to extend the lifespan of flies and even mice by dramatic amounts, even 30%.
So in mTOR, we start with fasting, we get longevity. In sirtuins, we start with fasting, we get longevity. In AMPK,
Same thing.
same thing,
But in this,
but in a different process.
exactly, it's doing something else.
Right.
And in this case, when you're hungry, AMPK will go up. AMPK, if you're wondering, it stands for AMP activated kinase, and that's just an enzyme that responds to low energy. So when you're hungry, you'll make more of it. And one of the main things that it does is it makes more mitochondria. We lose mitochondria as we get older, and when we exercise, we get more. And this is a way of artificially stimulating that production. Why do we need more mitochondria? Well, they're important for metabolizing things that you eat, but one of the main things that they are used for is to make energy, chemical energy. So when you activate AMPK, you'll feel better, you'll have more energy, and you also fight aging.